Hey, this is OXDF, and today we're doing the Advent of Code 2015, Day 19, Medicine for Rudolph, and we're doing it in Rust. We're doing this to learn Rust after many years of doing Python. So, um, disclaimer up front, this is the first day I've really kind of given up on writing in like a, I'll say, Rustian way and just could have like pulled together a really hacky solution to get the answer because frankly, it was kind of a hard day. So, let's take a look at the prompt. Basically, there's a bunch of story here, but what we're going to get is two things. We're going to get a list of element replacements that look something like this, but it'll be a lot longer. So in this case, H can go to HO, H can go to OH, or O can go to HH, noting that, H can go two different ways. And then we're going to get a starting string. So again, where ours will be 100 characters instead of 3, but, HOH. And so they point out in this example that there's 5 single replacements that can be pulled off. There's two ways, two replacements here, one replacement with the O, and then 2 replacements on the back H. But the resulting elements from those 5 replacements actually produces 4 different elements. So you can see this first one and the fourth one are the same. So we need to be cognizant of that as we work through. And so there's 4 distinct molecules generated. That's basically it. They want to know after one replacement, how many distinct molecules can be created. So let's jump over to VS Code and get started. I'm going to use my GenDay script here for day 19, and that will create, I go into detail exactly how this works in the introductory video I did, but basically it's going to give us input.text, which we'll have here, all these replacements, as well as our starting string, and then we will have our main, which we can start working from, and it just reads it into data for me. So let's go ahead and get started. The first thing I need to do, again, I'm going to do this very just one big main function with a bunch of stuff happening because it just, there might be an object-oriented way to do it, but I couldn't, for this one, again, string parsing in Rust is just a pain. So I kind of just went for getting it done. So first thing we're going to do is we're going to need to split the string into the elements, the replacement strings and the element. So we're going to do let, and we'll do like rep strs, comma, element equals, and we can do data dot. Now, if we did a data dot split here, we would actually get a problem because data dot split is going to return an iterator over an unknown number of things. But if we do split once, now we can split on, new line, and we're going to get back a tuple. Well, actually, right now we're going to get back a result or an option, I believe, but we can unwrap that. And now we get a tuple. Let me fix my... All right, that seems to be working better. So now we can see we're getting back 2 strings out of that. So perfect, that's just what we want. Now we can process that. So the first thing we did was, we've got our element. Now we need to take our replacement strings and process them. And I'm going to use a HashMap. So we need collections, and I'm actually going to import HashMap and hash set here because I'm going to use both here. All right, and so now we can do let map equals, and we'll start with rep strings dot lines. And now what we're going to do with these lines, the first thing we're doing is we're going to put a map onto them. So for each line, we'll call it L. We're going to L dot split once, just like we did before. And the delimiter this time is going to be this kind of arrow key thing. And then we need to take the result of that and unwrap it. And that will return, hopefully, we save this. Now we can see map is an iterator over a tuple of strings. So we're getting back a tuple of strings, which is what we want. Now what we want to do for each of those, we'll use the fold function here. And fold is going to take, see, does it give it to us? So there's it takes in 2 things. The first thing it takes is a iterator, or a initializer. So what do we want our accumulator to be? And in this case, we want it to be a hash map, and we'll just make a new one. And now, and we'll probably have to define what it is. So we'll say, and this hash map is going to be it's going to take in a string, so it's going to take in an element, and it's going to return a vector of strings. And the reason we need the vector is because, as you could see here, H, when I get H, it could turn into a bunch of other things. And so I need the ability to say H has all of these things in a vector, or else I'll just lose that. Okay, so now we've got our... We've initialized our accumulator to be a hash map. Now, fold takes a function. So the function, first we give it the inputs. The inputs are going to be the accumulator. So we'll call this, shouldn't probably call it M. And then so the accumulator is just going to get passed in each call. And then the other thing is going to be each element. And so in this case, the element that we're going over here, we already know is, well, it was before an iterator over string string. So now we need to give it what our string is going to be. And we'll call it like L and new L. Getting very creative here. And so now that function, how are we going to handle that? We're going to do map.entry for our hash map, and we'll say L.toString. So we're going to pass that entry in, and then we can say dot modify, oh, not dot and modify. So we get back, so we get our entry, and we're going to modify it by taking A and A.push, this is our vector, new L.toString. So we're going to push it on there. So we're going to say for each item in our list, we're going to fetch up our HashMap entry for that item, and we're going to modify it by pushing onto that vector the new element. Now, if that doesn't exist, so if we go to fetch that entry and it doesn't exist, we're going to create a new vector, and that new vector is just going to have new L and toString. So now we've created that. And if we save this right here, it's going to complain because fold, each time you call the function, is supposed to return the iterator, and we're returning nothing. So now we just need to come down here and do map again. So now we are returning them with the iterator. I bet you, let's see, what's it unhappy? Not map, M. Like that. Sweet. So now we're completing our fold. And so what's going to happen here actually is, so we're taking our lines, we're splitting them, and then for each one, we're iterating over it, and we're adding them to a hash map, and then we're returning that hash map, which we get up here, and we can see the types worked out. So now, I guess we can, that'll work, yeah. Okay, so now we've got our map. That's great. So now we need to loop over things and handle looking for it. And this would be so much easier if all the elements were single characters. I actually considered a solution where I would go through and replace all the elements with new element names, call them you can do emojis if you want, but make every element thing just a single character. But I decided against it. I felt kind of hacky. Oh, we were going with hacky here as well. So we're going to do for I in 0.element.length. So we're going to loop over the length of the element one character at a time. And we can start off by just thinking about one character. So we'll say let s equals, and that's going to be element sub I, comma, I plus 1. And that's effectively going to give us a string here for s that is one character long. And so now what we're going to do is we're going to say, is that in our map? And we're going to handle it differently if it is and if it isn't. So we're going to say match map.get s, like that. And now we can do some, we'll call it like rep replacements, some replacements. We do some stuff. We'll put that there for now as a placeholder, and then we can do none as like our default case, and like that. And now we have a thing. Let's see, what do we need here? String, it doesn't like that. Let's make it a pointer to a string, and now we look good. Okay. So when we find, let's make this start handling it. So we found some replacements, and so we have a vector of all the replacements for that character. So all we need to do now is we can say for r in replace rep. Now for each one of those, we're going to create a new string. Let mut new L string equals string new, like that. And now we will say new L string dot push string, and we're going to push on up to I. So the first part of the element string. So we'll say element and dot I, like that. And we don't like that. What don't we like about that? We expected okay, we expected that, we'll get that. Let's solve it, yes. Next, we'll push on the replacement value. Push string R, like that. And then finally, we'll do the same line again. But this time we're going to do from I plus 1 to the end. So we're pushing on the rest of the string. And now all that's left is we need to keep track of that. So we'll come back up here and we need to do like let next elements equals hash set new. And we probably need to say what kind of hash set. So we will do, I think we can just do string. That. Okay. So now whenever we create one of these, we're just going to do next elements dot insert, and this is where hash set's really valuable because we can insert as many times as we want, and then it'll just save it once. Element string. And what doesn't like about that? It needs to be mutable. We should make it mutable. And we should do that. All right. So we've handled the case now where we get one character elements, but we actually need to make this a little bit more flexible. So we're actually going to do for j in, and this is just like, again, kind of hacky, but 1,3. And now we better insert all of that and then put that there. So, okay, so now we're going to do this for j. We're going to do it twice for 1 and 2. And now for here, we're going to say let element equals I plus j. And down here, instead of going from I plus 1 to the end, we're going to go from I plus j to the end. And the one other thing, so the other thing we need to take into account, though, is what happens when, like, let's say our thing is 5 long. So I is going 0 to 4. The valid element substrings go to 4. That works fine when I is 2, when I is 1, but now that we made I2, we may try to read past the end of the array when we get to this part right here. So we need to make sure that this is, let's see, we can do, what's the best way to do this? We'll say if I is less than or equal to element dot len minus j. So basically, can we keep ourselves in there? We'll make it this. Else, and now, and we don't need a semicolon there because we're kind of returning the value. Else, we'll just do like an empty string. And that way, that's not going to match for sure. And we can just be moving on. So what do we like here? We need a thing. Cool. And that actually, I think, makes us good. Let's roll the dice here. Now we can come down here and say next elements.len, and that will be our part 1 result. So let's cargo run release this, and we get 518. And we get 518. Sweet, that's awesome. So we got it. Again, it was super kind of hacky, but we'll go with it. It's going to get hackier. Apologize for the cut there. My computer actually crashed, and I was just starting into part 2, and so I'm just going to pick it up right here at the part 2 description. So in this version, now we're calibrated. So we're almost going to do a completely new problem here. The basic idea is that every element starts from an E and is built up using the rules. And so what I need to do is take my puzzle input, which was this long string here, and figure out how many steps backwards to get to a single E. And so we could do it by starting with E and trying to apply all sorts of rules and doing like a recursive call down, but I think it's going to get huge and it's probably too many solutions to deal with. So I went for a solution that is not guaranteed to work, which is just so I'm going to start with the string itself and start to make replacements. And now I could do a thorough replacement where I'm going to try every possible replacements and in different orders and work down and do some sort of recursion with maybe like a caching to make sure that if I get the same string, I don't branch off a million times. But I'm going to try an assumption at the beginning. And my assumption is going to be that if I always try the longest, I always look for the longest one of these strings and replace it first, that hopefully I will get to the shortest path to E. I guarantee you that's not guaranteed to work, but I think it actually will work here. So let's go ahead and dive in. So the first thing, we're basically throwing away part 1. We're going to learn from it, but we're not going to use any of it. So we're going to need to reparse the input. So we'll do like, we need a dictionary now, or a hash map that takes us from an output to an input. So it's kind of the inverse of the previous one. And so we're just going to do re-parsing here. So we're going to do data.lines. Now I want to filter, and so that I only get the lines that have the like instructions on them. And so we'll do l.split. Oh, sorry, filter is not l.split, it's l.contains. So we only want the lines that have these equal arrow signs on them. So now that we have just those, and we can double check this, we see. So now we have an iterator over some strings, still what we want. Okay, so now we can map Now we're going to, just like before, we're going to turn that line into, we're going to split it once. And just like above, we split once on the arrow with the spaces. And now we need to unwrap that. And if we save that, we get a failure. What don't we like? Found. Does that look wrong? Comes from data lines, filter. Oh, because we don't need the, there we go. So that looks good. We don't like the unwrap here. It just helps if you spell unwrap correctly. Okay, so now we've got this tuples coming back, basically. You can see it's an iterator of string tuples. And now let's go ahead and fold those all together. So we'll use fold. And remember, fold takes it, first we define our accumulator. So we're going to use a HashMap. And we'll just use, we'll probably have to give it a type here. So in this case, we're going to be a little bit simpler this time. We're just going to do string string. I don't think there's any duplicate outputs. By that I mean, like, before we had to worry about that H could go to like 10 things. I don't think there's anything that HCA comes from but H. So we're gonna make that assumption. So we're gonna do that new, and now we've got our new hash map. So now we're gonna put our function here, and our function, let's see, is going to take in, I'll call it M, which will be our accumulator, in this case a hash map, and then we know it's gonna get passed in the element and the new element, just like that. And then so those are the arguments in, and then the function itself, we're just going to do m.insert, and the key is going to be new element. We'll say dot toString, and the value is going to be element dot toString. Okay, so basically we're going to loop over each set of new and old and put them into the hash map, and then just like before. This, we need to actually return M here so that we actually get that back. And so now we have a hash map of string string. So as this all worked just like we wanted to, perfect. The next thing we're going to do, let's see, I think we'll probably put that back one. The next thing we're going to do is we're going to get our keys. And so let's do let keys equals comes from keys. And then we're going to iter. And then we're going to collect into a vec of, and those are going to be strings, like that, I believe. It'll tell us if we're wrong. And we do that, like that. So now we're going to get iter. It doesn't like iter here. No method name iter for keys. I think we can do into iter. That works fine. What don't we like about collect? Run it and see. You've typed vec string cannot be built from pointers to string. Let's try vec string like that. Is it happy there? No. What if I just give it whatever it wants? All right, that's happy. So now it's a vector of pointer to strings. Cool. We'll work with that. Oh, now we want to sort the key. So no, I always want to like add this to the chain, but you don't. It has to be its own thing. So we're gonna say keys equals no, not keys equals keys sort by, and now we take A and B, and we want to do b.len dot cmp a.len. That, and it's gonna yell at us. Let's see, a.len. What do we need here? We need to borrow. Cool. We need to make this mutable. And we're good. So now we're going to have a sorted list of keys. Let's make sure that works. And I call these keys, these are really outputs. So let's see, this looks about right. We have it sorted. Here's the longer ones going down to all the 2-character ones at the end. So that looks good. Now technically, like this one is only 2. And one of these could be 1, but again, we're going for close enough here. We'll see if we can get a right answer. And again, if we can't, we should highlight that as a place to come back and look. So now what are we going to do? First, I need to start with my string, my element string that I use up here. I want a mutable copy, and I think I'm just going to create myself one. So I'm going to make let working equals let mut working equals element dot clone. Let's get ourselves a copy. And now I also am going to need let mut count equals 0 because we're trying to count how many steps we go. So now we're going to do a loop. And in this loop, what are we going to do? We're going to say for k in keys.iter. I'm going to say if working.contains k. If working contains k, then we're going to let from e, it's not capital E, e equals comes from dot get k dot unwrap. So if k is in the string, we're going to get the thing it came from here. Then we can say working equals working dot replace, oops, not repeat, replace, and we want replace n. And the reason we want replace n here is because we want to replace one time. Because let's say the thing we found is actually in there 3 times. We want to replace just once here because we're going to need to count. And we know the easiest way to count the number of replacements is just do one replacement. So we're going to do k. We're going to replace k with from e, and we're going to do it once. And I got a lot of red in here. Let's see if we can fix. Oh, okay. Let's see. So it's a pointer string. So we might need to dereference it twice. Is that what it's telling me to do? Consider borrowing here, like this. I would have definitely told you that these two would like cancel out, and maybe they do. Okay, looks like they do. So we'll do that there, and now we are going to. What's wrong with this? We probably still need to do a pointer to k here, and what else? Expected a string, found a string. Let's see, is it this one we need to put a pointer in front of to make a string? Type string, course to string, that looks good. Mismatch types, found struct string. Maybe I should do as string here. Or I could do, oh, why don't I make the element here? Let me do this. To string. That solved a lot of problems. Okay, perfect. So now I've updated my working. I need to update my count as well, plus equals 1. And now I'm going to break. And what that's going to do is basically, as soon as I find one that's in there, the longest one I find, I'm going to replace, and I'm going to go back and start over and check and see if the longest one's in there again. If that all worked well, we should be able to just put count here, get rid of our debug print. Oh, we got one problem. This is an infinite loop. We're never going to break. So when do we want to actually end? We want to say if working equals e, break. So basically we want to break when we're finished. And now if this runs infinitely, that means we probably didn't solve it, but it doesn't, and we got an answer, and I think that's the right answer. Let's check it out. It is. So awesome. Parsing strings in Rust and like doing all sorts of string manipulation is not super fun, but we made it through it, even if it's kind of a hacky solution. Thanks for sticking around, and I'll talk to you next time.